you enjoying watching me work hard type of day. So we've spent, the last couple of lectures were quite formal or abstract, and it can be quite easy to sort of think you followed something, but until you actually try and calculate, then you don't know for sure whether you've really understood it. And of course, normally we would sort of get you to do this sort of hard work offline, but with all, the pressure of a lecture every day and everything else that you've got to do, I think it's easier if I go through this at least once, so you kind of see how you actually apply those Cartan equations to something a bit more general than just R squared or S2. So here we're going to look at a spherically symmetric metric so that we can at least end the lecture by talking about black hole solutions. So a black hole is the sort of endpoint of a very heavy star, or possibly it's something that was created in the early universe, but it's basically round. It's roughly spherical. Now, black holes usually rotate, but just for the moment, let's not get ahead of ourselves. Let's just do the simplest possible case, where our black hole, we're saying basically it's non-rotating. So it's just an isolated object. You've seen this solution already, the Schwarzschild solution. So let's look at how we get to that through using Cartan. So we're going to start with our ansatz, as I think in the notes that David has latexed up. There's a sort of commentary on how you get to this coordinate system. You use that SO3 algebra of Killing vectors, that's the spherical symmetry part, to choose two angular coordinates. So here we've got the metric on the unit 2 sphere, which we usually denote as d omega. And I'm starting off in a somewhat more general gauge than you might have seen, simply because in some applications, when you're looking at more general black holes, not just Einstein gravity, but modified gravity, you may find, for example, C can doesn't always have to be increasing. So you can get wormhole-y type of solutions with C. And sometimes it's advantageous not to have B being 1 over A. So at the moment, I'm just going to keep it general. This is over general. Okay, there's still a gauge degree of freedom hidden in here, but let's just work forward. So to apply Cartan, we need an orthonormal basis. So let's find, it's fairly easy to write down in this block diagonal metric, but let's write our orthonormal basis of one forms. So we can see pretty much straight off what these are from this expression. Our omega t is A of r dt. Omega r is B dr. Omega theta is C d theta. And omega phi is C sine theta d phi. So we just read that off, really, from the metric. That bit is straightforward. So our next step is to find the spin connection. And we do that by taking the exterior derivative of our basis of one forms. So d of omega t is A prime dr cross dt, and that's A primed over AB, or minus A primed over AB, omega t cross omega r. So, not particularly hard, but we know that this has to equal minus theta ta cross omega a. And so we guess, and we'll just make sure it makes sense at the end, that tells us that theta t r is equal to A primed on AB omega t. And all the other t theta t phi are 0. So this is the only non-zero connection component. So d omega r is 0. So let's just think, if this, remember, our connection forms are antisymmetric. So theta RT is going to be up to a sign the same as theta TR. So if I look at theta RT cross omega t, that does indeed vanish. So there's no inconsistency there so far. Now, if I look at omega theta, you can see that it's going to run through pretty much the same as omega t, but with the t replaced by a theta. So I can sort of follow the same steps here, kind of substituting a theta for this t index and a c for the a. And I'm going to end up with the same component, same sort of pattern down there. And then finally, d omega phi is c prime sine theta dr cross d phi plus c cos theta d theta cross d phi. So I have two connection components here, two non-zero ones. And so it's not too hard to see that the only non-zero ones are a phi r and a phi theta. So the details are in the handout, but essentially all we're doing is taking derivatives, comparing to that Cartan equation without torsion, and then reading off what the spin connection has to be. So these are all the obvious non-zero terms, plus things that are gotten by symmetry. So just to put as an aside, we're going to need, let's say, theta r hat, theta hat, are basis indices. Remember that we've chosen an orthonormal basis. So that means indices are raised and lowered with the Minkowski metric. So this equals eta r hat a hat and eta theta hat b hat actually let me just do this. So if I need to find theta r theta, first of all I say I've raised the r index here. I then swap the ordering of indices here to pick up a minus sign. And then I now want to sort of, this means I've raised the r index, I've lowered the theta index here, but we know that the only non-zero components of eta are when A equals R and B equals theta. So this is minus theta, theta R hat. So that's how we get the other non-zero spin connection. Yep.
So the indices on the theta, though, aren't tensor indices? So,
no, they're not.
So when you're raising and lowering them with the...
They're components, yeah, they're scalars. Let me...
but like, if you're raising and lowering them with the metric, is it because... I don't understand.
It's okay, right. So let's take a step back and think again. This is still rooted in this question or this issue of what do the labels mean? Yeah, it's the same issue that we're confronting. So if at this point, if we write down an index, it is just like a label. So at the top, when I wrote down the basis of one forms, that index, T, R, theta, phi, is telling you which one form it is. So it's counting through T, the different basis vectors. The reason I put a hat over the index was to try and emphasize that this was a label for an orthonormal vector. So we know that the t hat omega is associated to the coordinate t, yeah, because that's how we built it. But but that's our sort of behind the scenes knowledge. In essence, I could have called this omega 1, 2, 3, 4, omega dog, omega cat, omega rabbit, omega hamster or something. It's an arbitrary label at this point. And so I tried to put the hat on because otherwise it's easy to kind of think, oh, that is the coordinate index, okay? So then we ask, what are the theta ABs? So they're a matrix of one forms. The geometric part of it is the one form, and the indices, the R, theta, or AB, represent where they are in that matrix of one forms. But they're also, every time you see one of these hatted indices, if you sort of see an object with these kind of hatted indices, that's saying that you've decomposed it with respect to this particular basis. So when you write down the connection, it's always the connection with respect to this particular basis. And so therefore, when you are raising and lowering these sort of orthonormal basis indices, you have to kind of do it with the eta. So you're always either taking the index down with a +1 or down with a -1. It takes some getting used to.
Is it with like the coordinates in Minkowski that they are not vectors, but you can still like lower and
Sorry,
is it like with the coordinates when you're in Minkowski space? But they're not vectors. Coordinates are not usually
X, Y, Z, yeah. Mm-hmm.
But you can lower and upper the components with the metric. Is it similar to that?
Yeah, I'm not sure I know exactly what you mean by that. So...
I mean, when you're in Minkowski spacetime, you can take like the coordinates like x mu, for example.
Yes.
And in GR they are not like...
Absolutely, they're just a point, yeah.
They're just a point. But in Minkowski we treat them as vectors because...
Yeah.
I don't know why. I'm just saying...
Well, it's because if you're in... But only for Cartesian. Because in Minkowski space, if you're in Cartesians, your basis just goes all the way around, parallel transports everywhere. So that means that there's a complete equivalence between the vectors and the points.
Because you build them in a way that it's like... You kind of like hide the curvature in the elements of these spaces. Is it like...
I'm not sure, because I'm not sure I'm getting what you have in your mind when you say that. Okay. So it might be, but I'm not quite sure what you've got in when you ask the question. I'm not sure what's in your mind. It's basically the hatted things are labels in the frame, and so in that frame everything's orthonormal. I don't know. Gradually, as you do more and more with this, it makes more sense. So I'm not sure that just by talking I'm going to make it any clearer at this point. I think by doing it might be a bit clearer. So I've got the spin connection now, and now I want to get the curvature. So the curvature 2 forms are antisymmetric for the metric connection. So we kind of know that there's a limited number that we have to calculate. So we only have to calculate 6 of them. We've got 1, 2, 3, 4 non-zero connection forms. So let's just get on and calculate. If I start with RTR, that's just going to be d of theta tr because there's no cross terms. Remember that our relation for the curvature 2 forms is that RAB is d of theta AB plus theta AC wedge theta CB. So that's what we're using. So you can convince yourself there's no cross terms because there's no way of having a T here and an R there where both of these are non-zero for the label C. So this is d of A primed on B dt. So we have that as A primed on B primed dr wedge dt. So when I go back to writing it in terms of my basis, I have to sort of put in sort of the factors of A and B, which take me from dr and dt to omega r and omega t. And you'll notice I've just swapped the ordering, and there's a minus sign there that doesn't look very big, so let me emphasize it a bit more. So that now gives me Riemann components starting in T and R. And I carry on. I've got T theta. Now there's no spin connection with components T theta, but what I do have is a spin connection component with TR and a spin connection component with R theta, which we just said was minus theta r. So if I now substitute what those are, I get A primed over AB for theta tr, and then I've got minus C primed on CB for R theta. So here I've now got my Riemann components beginning with T and theta. And you can see that if I replace the theta with a phi there, I get essentially the same thing. So I'm actually halfway there, because there were only 6 independent components, and there's 3 of them. So now let me look at our theta hat r hat. So I put this down because you do have to actually think about whether there's any cross terms here. So if I look here, the non-zero values where I've got a theta hat index of the spin connection, if I look at the top board, I've got a theta phi theta, which is proportional to omega phi, and I've got a theta, so if this index here is a phi, that would be theta phi with phi r, but both theta phi and phi r spin connections, which are in the bottom right-hand corner of the top board, are proportional to omega phi. So this term doesn't give me anything, so I can ignore it. And then I look at the theta r term, which is c primed over cb omega theta. So that's c primed over b d theta. And you see that it's coming out to be exactly the same pattern as this, but with a C instead of an A. So I guess what we're finding here, or one of the lessons, is that quite often you find patterns. So although you have these different coordinates, t and theta, one's time, one's space-like, because the way in which they appear in the metric is very similar, they're appearing as dt squared times a function of r or d theta squared times a function of r, the way in which the calculation goes through for the spin connection and the curvature 2 form is extremely analogous. You're basically just substituting symbols. You're substituting the function, you're changing the label. And so you're not actually doing the calculation entirely from scratch. You're sort of repeating something that you've already done, but with things juggled around a bit. So what you start to see with this formalism is you start to see patterns when you're calculating with a metric. So you're not sort of doing each component separately, or completely, from the start. You're kind of seeing, well, this looks like this, even though the coordinates mean different things. One's space-like, one's time-like. You're kind of seeing that the way in which they contribute to curvature is nonetheless the same. So that's number 4. Number 5 are phi r. I now actually have to think about the cross terms, because the phi theta spin connection component is proportional to omega phi, whereas the theta r one is proportional to omega theta. So let me now write what this is. So phi r is c primed on b sine theta d phi. Phi theta is 1 over c cot theta omega phi. And theta r is c primed on cb omega theta. So now I look at taking d of this. So I'm going to get a c primed on B with respect to r. So I get a term that again looks very much like what's going on over here. And I've got plus c primed on B cos theta d theta cross d phi. And over here, if I substitute what these things are, that is c primed over B cos theta d phi cross d theta. So this term and this term cancel each other out, and I'm just left with, again, the same piece as you get with the theta component. So now I finish off. And once again, two terms contribute. So this is d of cos theta d phi. Yeah. And so I just substitute in what the one forms are for phi r and r theta. So this first term is just minus sine theta d theta d phi. And I'm done. So I've computed all of the curvature 2 forms now, which means reading off, in this case, reading off the Riemann tensor is relatively straightforward. So the first term, the TR, I see here, TR is just, has this functional form. If I go back to the next thing I did, T theta, T theta. That's what I get. And similarly, that's the same as T phi, T phi. So now I go here, theta r, still with a minus sign. And that is also going to be the same as r phi, phi r. And finally, I just read off from here. I've got 1 over c squared minus c prime squared over c squared b squared. So that's it. So I've now finished computing the Riemann tensor for that metric. So it's a bit of a calculational slog, but it is nowhere near the same amount of slog as if you'd gone through computing the Levi-Civita connection components and then gone ahead and differentiated those and combined them to find the Riemann tensor. Now, coming back to this issue of labels, which I agree is, takes some getting used to, notice all the hats there. Those labels indicate this is the Riemann tensor in the orthonormal basis, not in the coordinate basis. I made a comment somewhere here. So what happens to go from orthonormal basis to coordinate basis? You've kind of just got to remember what things mean. So let's say we're looking at the Riemann just as a geometric object. That would be A, B, C, D, EA, omega B, omega C, omega D, because it is a rank 1-3 tensor. So this would be how you would construct that tensor. You'd kind of, here are the components. And here is the sort of tensorial part. And so the components would be what I've written up there. But now we're very used to doing things in a coordinate basis. So how do we write that in the coordinate basis? Well, we kind of recall that our EA we could write as EA mu d by dx mu in a coordinate basis. And so these here, this is the sort of Vielbein or Vierbein. These are the components of the orthonormal vectors in a coordinate basis. And similarly, omega A would be omega A mu dx mu. So you might, if you get into the supergravity literature, what you'll probably notice is that both E's and omegas are actually expressed as E's. I prefer to keep them separate to distinguish, the fact that one comes from being a basis of one forms. So that means to get to the coordinate parts of Riemann, we simply multiply by those components of the basis one forms or basis vectors in the coordinate basis. So loosely speaking, you'll see that the E's and the omegas kind of cancel each other out. So I guess if we just do it for detail for the RTR TR term, that would be equal to ET hat T, omega R hat R, omega T hat T, omega R hat R, R, T, R, T, R. Hatted. And so this here is 1 over A, this is B, and this is B. So we just multiply by B squared there. Alternately, what you can do is simply raise the indices like so, and then you have two E's and two omegas that end up cancelling out. So just having done that, so that is the Riemann tensor in coordinate basis. So from that, if we're interested in our spherically symmetric vacuum solutions, or not even vacuum, what we would take from this is that RTT so here our curvature in the t direction, obviously its headline part is the second derivative of the function multiplying it. So, you know, A is telling you how time scales as you move from one radius to another. So the bulk of the curvature there should be telling you about, you know, the sort of the second derivative of A. But you also pick up these cross terms, and you can kind of see, I mean, the B is perhaps not so relevant because that's part of the gauge choice of R, but you see for each of the coordinates on the two-sphere, the theta and the phi, you pick up this cross term, A prime, C primed. So in the theta, it's got exactly the same pattern. It sort of kicks off with this second derivative of the function multiplying these coordinates. It then has a cross term coming from the fact that both gtt and g theta theta depend on R. And then there's a second cross term, which is the fact that both g theta theta and g phi phi depend on R. And then this term, the minus 1 over c squared, this is actually coming because it's a two-sphere. So the curvature of a sphere is 1 on L squared, or the radius of the sphere. So that's what the last piece is. So we're interested in solutions that are spherically symmetric and static. So we simply have to equate this to the appropriate combination of energy momentum tensor. Now at this point, I want to just try and restrict my gauge. So we sort of just comments on the gauge that you might choose here. One gauge would be C equals R. That's what you're used to. So this is the area gauge. And that means that what your coordinate R is telling you about area of spheres. It's not really a proper distance. If you want R to be a proper distance, you have to set B equals 1. So that would be a different gauge. Sometimes you set A is 1 on B. So that's, if you like, the Schwarzschild gauge. Sometimes that makes the equations work well. And then another thing that you do is you may set C as rho or RB. And you do this when, so if you're trying to find the ADM mass of a system, you go to a coordinate, I'll call it ADM gauge. You kind of want to go to a coordinate system where your spatial part is some overall multiplicative factor times your flat space polar coordinates. So sometimes you want to write things in that gauge. Overall, though, the message I wanted to get across here was really that the Cartan formalism is actually computationally quite light or straightforward. All you're ever doing is taking derivatives, and this exterior derivative d really just acts like sort of you would expect. I mean, I haven't done anything mysterious here. I've just said, you know, well, d of a primed on b dt is the derivative, radial derivative of a primed on b times dr cross dt. It's very, very straightforward differentiation. And there's a sort of semi-proof of that. If you've ever sort of given any presentations or teaching, you'll know that if you actually try to do a calculation in real time in front of people, it's much harder than doing it yourself on a piece of paper. So if this can be done in front of an audience, you know, on a blackboard, it means it's not that hard to do. So I just want to kind of try and get across. This really is a dead easy way of calculating curvatures. So let's have a look at some solutions and talk a little bit about them. I'll come on this theme before. What I want to do is to take the area gauge, because that's really what we're familiar with. C is R, C primed is 1, C double primed is 0. So a lot of simplifications then occur in the Ricci tensor. And when we do that, we find that the TT component becomes quite straightforward. So you see that with the C double prime dropping out, say like RTT, there is A double primed on A, the A prime B prime piece, but then it's 2 A primed on AR. So the reason I've pulled out this is that obviously GTT is related to energy density, and it's expressible as a derivative, total derivative. So I can integrate up for that function, the radial metric function in this gauge, and it's something that looks really rather familiar, because 4 pi r squared is the area of a sphere. So 4 pi r squared dr is the volume between r and r plus dr. So this integral, in some sense, is telling you how much energy you've got. inside a sphere of radius r. So we can interpret physically what our B function is. It's telling us about how much energy is inside our spheres. So if we wanted a vacuum solution, then we would, if we were being completely general, we'd pop in an arbitrary integration constant, and we'd say, well, b to the minus 2 is 1 minus 2 gm on r. We'd also look at, if I look over here, look at the top and bottom Ricci, they both start with a double primed on A. This term isn't there because C is R. Here's an A prime B primed on AB. And so the only way they differ is in this last term. So in vacuum, this is also 0, which tells me that A is proportional to 1 on B. And so we get the Schwarzschild solution. A squared is B to the minus 2 is 1 minus 2 gm on R. So that's sort of having derived, we've gone all the way from our initial metric through calculating the curvature, through solving the Einstein equations to get our simple Schwarzschild black hole. So I just want to wrap up today by, I know you've seen Schwarzschild, and I also know you've seen de Sitter in cosmology, but I want to kind of pull those two strands together. I'm not sure you've seen black holes with a cosmological constant, at least not in the lectures. So I want to kind of wrap up by talking about the cosmological constant. So the cosmological constant was introduced initially by Einstein right back in the day when he was first putting forward general relativity. So at the time, there was actually evidence at the time for the expansion. So prior to Hubble, Slipher had got observational data sort of indicating redshifts, but I think it was all a bit sort of, suggestive rather than definitive at the time. And therefore, people, I think Einstein in particular felt if he produced a theory that said the universe was expanding, it was kind of going to just, be put on the shelf. It wasn't going to be taken too seriously. So he wanted to be able to get a static cosmology, and therefore he introduced this constant energy density throughout the whole of space and time. So the cosmological constant you can view it as an effective energy momentum tensor, which is, I would say, how we view it now. It's just saying that energy and pressure, the whole energy momentum tensor is proportional to the metric, and it's just a constant. So that was what he did. By adding that extra piece to his equations, I think he added it more to the Einstein tensor rather than viewing it as an energy momentum source. It was simply, well, this constant is completely consistent with all of the principles of the general relativity, and it allowed him to get a static universe. But, of course, very soon after, the data started weighing up on the side of having an expanding universe. And so although de Sitter, just months after GR came out, produced his solutions, which were exponentially expanding, bit of an irony, having put a constant in to make a static universe, to find it generically makes it exponentially expand. They sort of ended up on the curiosity shelf, like Kaluza-Klein theory ended up on a curiosity shelf of gravity. It's fantastic, all very interesting, but nothing to do with the real world. So I don't know, I think Einstein might be quite chuffed to see that we do have a lambda today, but anyway. So if we actually look now at putting in this source to what we just did, that means we're substituting T00 is a constant in that integral. So that integral is going to look like R cubed. If we look to the right with that relationship between the Ricci components, that's also going to be true with a lambda. So RTT still equals RRR, even when you've got a cosmological constant. So that tells us our solution still has A proportional to 1 over B. My integral of 4 pi r squared T00 is lambda over 2g times the integral of r squared. So we get lambda r cubed over 6g. And that tells us our solution in general has this form. So we get just a minor change to our Schwarzschild potential, and it seems minor, with the quadratic term in R. So de Sitter put in a positive lambda, so that's what we've got in our universe today. And so if lambda is positive, both of these terms are negative. And so we're going to have a horizon due to the black hole mass, so somewhere where A goes to 0. But we're also going to have one at sort of larger r because of lambda. So as long as m, or the Schwarzschild radius 2gm, is much less than L, this is going to be approximately true. The horizon is going to be close to 2gm for the black hole. And there's another horizon at large values of r, which is at L. So this is the cosmological horizon. And so you would have seen this from a rather different point of view. So I can actually take m to 0 to find pure de Sitter, where my a squared is 1 minus r squared on L squared. Now, when you've seen de Sitter, for those of you that did the cosmology course, you would have seen a rather different expression of de Sitter, because you're probably sort of sitting there thinking, but hang on, our universe is very time-dependent, it's expanding, and I know that pure de Sitter space exponentially expands, so how come you've got this static solution here? And so the answer is, of course, gauge. It's choice of coordinates. And de Sitter, and also anti-de Sitter space, are examples of spacetimes that have many different ways of slicing, many different coordinate spacetimes. So de Sitter is a constant curvature space, and we can represent it as a four-dimensional hyperboloid in 5D flat Minkowski space-time. So if we have so this is what we mean. We take flat five-dimensional space-time and we embed a four-dimensional manifold. So here we're coming to this idea of embedding a manifold in the space-time with this one constraint. So that's what defines a hyperboloid. And the metric on de Sitter is inherited. The metric on this hyperboloid is simply inherited by projecting down the five-dimensional flat metric onto this four-dimensional hyperboloid. So for our static slicing, we take two coordinates and relate them to t and r. And r is just given as the length of the first three coordinates there, the capital X, Y, and Z. If you wanted in terms of a Friedman-Robertson-Walker approach, you've got global coordinates. So here you would say t was L sinh tau on L, u was L cosh tau on L cos chi, and then the x would be L cosh tau on L sin chi, and n. So this would give a closed universe, kappa equals 1 cosmology, and then you can also slice it to get the flat cosmology. So I'll just, which is probably what you're used to, which is that so between static to flat, just write this down, you're going to have to check it yourself. So this is the one where you have exponential expansion. So the message is there's many ways, because de Sitter has so many symmetries, there's many ways to coordinatize it, and the way in which you coordinatize it sort of depends on the problem that you want to solve. So I also want to talk about anti-de Sitter space, but I think that's probably better left to another time, because I think I've spent long enough. But it's sort of thinking about black holes with a cosmological constant starts to become quite interesting. If you want to think about primordial black holes, you maybe want to sort of think about what's happening, with the cosmological constant. The fact there are two horizons in de Sitter is kind of interesting. And then when you go to anti-de Sitter, which is with a negative lambda, which people really didn't bother too much about at all, except if they were doing mathematical GR until very recently. Anti-de Sitter has even more curious black hole solutions. You can have planar black holes and hyperbolic black holes. So we'll kind of be meeting all of these different sorts of black holes as we move forward.